Hi students, in this lecture let us discuss about Miller's and Bootstrap time-based generator waveform. So before going into the topic, by taking this two time-based generator waveforms, which type of the parameters we have to calculate means we have to calculate the output waveform, and next we have to calculate the errors which are occur in the output waveform. Okay, and next thing is you have to read first point here. From the previous sweep circuit, the linear sweep is not obtained because the current through the capacitor is charging. Again the capacitor is discharging after some time. Means due to the characteristics of the capacitor, the sweep waveform is generated. But in which waveform it is generated? It is not in linear shape. That is, example is exponential sweep waveform. In the previous lecture we have discussed. So to overcome the drawback only, we are going for the Miller's and Bootstrap time-based generator waveforms. Okay, the simple circuit diagrams of Miller's time-based waveform is given in this format. So you can see figure A. So I am taking the input voltage, resistor or capacitor C and switch S, same as your exponential sweep circuit. But what is the main difference between that circuit and this circuit? Means we are adding some type of the voltage at the input side as well as at the capacitor, at last at the switch. But whereas in the exponential sweep circuit, we are not adding any type of the voltage at the input side. So that makes the difference between your Miller's and exponential sweep circuit diagram. And next thing is, after drawing this simple circuit diagram, again we are doing some changes. So what are those changes? Means this parallel capacitor is converted into the series. Okay, that change is doing here. So here, see here, same term is there, but the capacitor in series connection is changed into the parallel connection is changed into series. Why I am changing this capacitor of parallel connection to the series connection? Means to avoid some of the errors or to avoid some of the discharging level present in a capacitor. So that is the main thing. So to provide, see here, to provide the constant current through the transistor, the voltage across the transistor equal and the opposite of the voltage should be generated. Means how much voltage you are applying at the input side, if the same voltage will be reflected at the output side, then we can know that the high level of your sweep circuit output waveform will be generated, and any error or any distance between your output waveform will not be changes. Okay, and next point is, after drawing that figure B, if we apply the Kirchhoff voltage law, then we will get V is equal to IR plus VC plus V. Okay, here VC means capacitor voltage, here V means input voltage. So at last V is equal to IR. In the place of VC I am replacing minus V. Why? Means according to the nodal analysis, how much voltage present at this node must be equal to the voltage present at that node. Okay, that is next thing. And if V plus V and minus V will get cancelled, we get V is equal to minus IR, I is equal to V by R. Means indirectly which type of the form of formula we are getting here? Means Ohm's law. We are getting Ohm's law. In the Ohm's law, the circuit analysis will be very good. You can apply any type of the circuit to calculate the current and the voltages. You can consider the Ohm's law. And next, depending upon this current only, that is constant current, the depending upon this constant current only, the sweep circuits are divided into two types. One is Miller's sweep circuit and another is Bootstrap sweep circuit. Okay, first of all we will consider the Miller sweep circuit, and the same as the Bootstrap procedure will also be the same. Okay, so Miller sweep circuit, the simple circuit diagram of the Miller sweep circuit is given in this manner, that is voltage, resistor, capacitor, again voltage. Okay, before only I have repeated this point. At the input side, how much voltage you are considering, the same voltage must be considered here also. Okay, and next thing is the voltage generator is replaced by the amplifier, which is shown in figure D. What is the voltage generator? Voltage generator means I am taking at the capacitor, that is VC. This total term will be replaced with the help of the amplifier. Which type of the amplifier I am taking? Voltage amplifier. In the voltage you have to consider the VC voltage. So again the term is changed into the voltage amplifier, that is V in capacitor VC, and how much voltage at the amplifier will be there means infinity voltage will be there, means this total term is changes into the voltage amplifier, which is represented in the form of A. And next I want to calculate the voltage, that is amplitude. I am telling that amplitude, but you have to calculate the voltage. So output voltage by input voltage. What is the output voltage here? V naught by V in. But here how much voltage I am taking? Minus infinity. That is, it may be nearly equal to more value. So I have to replace some of the resistance value which is equal to the above Ohm's law. That is, input V is equal to minus IR is equal to V. That is, V is equal to IR. V is equal to IR, then V in must be equal to 0. So that value I am replacing here, that is 0. So I am getting minus infinity. So I am replacing what is the amplitude means A is equal to minus infinity value. Okay. And next thing is, after completing this point, again we are going to the figure D. By seeing this figure D has input, that is I is equal to V by R. V in is equal to 0. Already we have calculated here. At t is equal to 0 plus means at initial time we are giving some type of the second value, that is some type of the voltage for the capacitor, but it does not change instantaneously, because at t is equal to 0 the switch is not closed, it is open, so we are not getting any type of the voltage. The gain of the amplifier will be given by A is equal to V naught by V in. Again we are substituting. What is V naught here means, here V naught is equal to, here V naught is equal to how much voltage present here at the node must be equal. So in the place of V naught I am considering the capacitor voltage VC, and V in will is replaced same. But here what is V in? V in is equal to 0. So here also we are getting the infinity. So next point is the amplifier which provides the infinity gain. That amplifier is known as the operational amplifier. Okay, but in this one we are not considering the operational amplifier, but this operational amplifier will act as a integrator. Okay, this Miller circuit is also known as Miller's integrated circuit. Why it is known as Miller's integrated circuit means, at the amplifier circuit how much voltage we are getting, if you are considering the voltage generator, infinity means n more voltage flow is there. So due to that more voltage flow only, this Miller circuit is changing, this Miller circuit is changed into the Miller's integrated circuit. Okay, after completing that Miller's integrated circuit, so again I have replaced that circuit with the help of some type of the voltage source, because I am considering in the voltage amplifier. So here the voltage amplifier is taken, input resistance and output resistance, which we are considering the first unit, that is voltage amplifier. So after considering this concept, again you have to simplify this circuit. So whenever you are simplifying the circuit, where R in, what is R in means input impedance of the amplifier, R naught is output impedance of an amplifier, and operational amplifier, that is voltage, and already we are telling that it is operational amplifier, but I am taking it as an integrator. If the input circuit is replaced with the help of the Thevenin's equivalent circuit, this circuit composition VR and Rin is replaced with the help of V dash and R dash as shown in the below figure. So what is the statement of the Thevenin's theorem? Any linear network is replaced with the help of voltage source in series with resistor. So that's only he has considered, means this total R in and R is replaced with the R equivalent, that is R equivalent is equal to R plus R in dash, but he has replaced into the R dash, and remaining capacitor is same, A into VI is same and R naught is same, and we have to calculate output. Okay, and next we are taking some type of the assumptions. Due to that assumption, which type of the output is generated here we have to understand. At t is equal to 0, the capacitor voltage is also 0 because it is initially the switch is open. Any type of the voltage will not be there, and the capacitor charging is also not there, so we are neglecting, that is V in is equal to 0. Then what is the formula? V naught is equal to A into V in. For the operational amplifier, that is for the voltage amplifier, output voltage is equal to some gain into input voltage. How means? A is equal to V naught by V in, already we had it, and next V naught is equal to modulus of A in, but already V in is equal to 0, means indirectly V naught output voltage you are getting, means that is 0 for t is equal to 0 second. But if you are considering for t is equal to infinity, then the capacitor is completely charged, then V naught is equal to modulus of V in, means any type of the input voltage will not be lost here, we are getting the maximum input voltage, so we are considering V naught is equal to maximum gain into V in. So what difference we have understand here means, when we are considering t is equal to 0, we are getting output voltage is equal to 0, but at the infinity condition we are considering V naught is equal to V in. So what we have understand here means, whenever you are taking any type of the voltage amplifier or the amplified circuit, so then we have to keep the maximum time constant value in that one, then only we will get the output voltage heavy. Then whenever the output voltage get heavy, then the sweep circuit waveform will be generated without any type of the distortion or any type of the noise. So that is one reason. So after calculating this thing, again we have to calculate some type of the slope error. So slope error, what is the slope error? Slope error, we are having some type of the formula. Again you have to substitute Es is equal to Vs by, again you have to simplify, then we will get some part, that is indirectly we will get this portion, that is V naught is equal to modulus A in into I into R dash plus R naught plus A into V in. So this is the how the output is generated at the t is equal to 0 seconds. And similarly the same thing for the bootstrap circuit is also same. So in the bootstrap circuit again we are considering the amplifier, but in this one we are calculating the sweep loop error, that is as the voltage across the capacitor is generated, it must be equal to the gain. So here in this bootstrap circuit, input voltage is equal to output voltage, so V naught by V in is equal to V by V, that is equal to 1. So what is the main difference between the Miller's and the bootstrap circuit means, in the Miller's circuit the input voltage will be nearly equal to 0, which we are considering one type of the assumption, but whereas in the bootstrap circuit we are getting input voltage by output voltage, that is gain is equal to 1. Means what do you understand means, whenever you are considering any type of the voltages at the voltage amplifiers, we have to consider maybe the Miller's theorem, and that is Miller's sweep circuit or bootstrap circuit, then only it can be understand the easy concept. And next thing is, this question is repeated number of times in your exam, and this question is very important, you can study well. Okay, thank you students.